Okay, are we recording? Okay. So as you can see, we have some winners for the first scoreboard. So basically, the winner is somebody called Pabloy, and then nicknamed Perfect Totient. Drop table students, well, thanks goodness, they have a little bit of SQL protection and a ladder. So those 5 will get some piece of chocolate next Wednesday if they come. So who of those 5 winners is actually here? Please raise your hands if you're awesome. Let's give them a round of applause. So tell everybody else that if they come on Wednesday, they can pick up a piece of chocolate and it'll be all nicely recorded for posterity. So what I'm trying to say is, from now on, the top 5 for any of the programming assignments will, get something. So there's a little bit more reason for you to do really well in the programming assignment, because otherwise, it's just boring. And what you could also see is that the same algorithm, just depending on how well you tune it, will give you quite vastly different performance, right? So the thing is, if you're somewhere there, you should probably ask what you're doing wrong. Up here, I'd like to know what Pabloy is doing right, because he's probably using all sorts of nice tricks. And so is Pabloy here? Oh, awesome. Actually, would you mind telling us, like in 5 minutes, all the things that you've done? So just give a bit of an idea and an overview of the things that you did. Do you mind coming up here? Okay, so this is, of course, totally unannounced, and Pablo had no idea whatsoever. So such that you're nicely on camera.
Hello, everyone. I'm Pablo. So what I did, other than trying a lot of different stuff with some cross-validation, so separating my train and test sets. So I trained the algorithm in one and tested for some other data points how well it performed. What I ended up doing is finding a distance that was basically depending on the Fourier transform of the data. So basically, I compute the Fourier transform of it and compute the distance between those 2 vectors in an Euclidean manner. What I did find that improved maybe 5 or 6 points in the accuracy was not to actually keep the Fourier transform, but other than taking the absolute value of the Fourier transform, so the phase did not help me at all to do the classification. I took the square root of the absolute of the Fourier transform, because if I didn't do that, the terms that dominated the distance were places where the Fourier transform was very high, and the rest of the Fourier transform became kind of irrelevant for that matter. So I tried a couple different things. I took the logarithm of the absolute value. That did not work so well, because everything basically starts weighing the same for the comparison. But at the end of the day, the square root was the one that gave me the best results.
Okay, so let's give Pablo a round of applause. Thank you.
Thank you.
Very well done. So, okay, let me just get my microphone again. Okay, so basically, one of the rewards for knocking it out of the ballpark will be that you get to talk for a minute or 2 about what you did. I don't know whether that's an encouragement or disincentive. I hope it's an encouragement. So really well done. What this actually tells you is the following, that using the machine learning algorithms themselves will get you reasonably far. However, in order to really then beat a record, you also need to try and understand the problem that you're trying to solve. If you're not doing that, then you will get good performance, but not amazing performance. So basically, by trying to become somewhat of a domain expert on your problem, you can do better. There's a question in the back.
What was the data? It looked like a time signal that was really big in the middle.
Yes. So talk to our TA. He can walk you through that. So basically, We will probably discuss this a little bit more in detail anyway in one of the recitations, because essentially we want to make it easy for people to understand what the homework was, what the idea was, because otherwise you just do the homework, and if you don't get feedback, it makes it harder. So, but basically what it shows you is that being a good engineer and then using the machine learning algorithm skillfully, both things are required to solve a problem really well. And this is sometimes why, if somebody tells you, well, company X is using algorithm Y, it doesn't really help you very much yet, because it's missing out on all the cool tricks that, for instance, Pablo did in this homework. Okay. So with that said, let's jump right into density estimation. And since we did this a little bit quickly last week, so this was basically just an advanced preview, I'm actually going to walk you through it in a lot more detail today. So we start with Parzen windows, and essentially we start with the issue of density estimation, that, for instance, if I wanted to build a classifier using Bayes' rule, well, it would be, in theory, amazingly easy, because all you would do is you would estimate P of X. You would also go and estimate P of X given Y. So at the very least, you would have to estimate P of X given Y and P of Y. And then simply by invoking Bayes' rule, it would be very easy for you to obtain P of Y given X. Right? So if we have a universal density estimator, we can just invoke that, and we get P of Y given X out of it. So in that case, if Y is a binary variable like apples and oranges, and X are images, then if I have a good generative model of what apples and oranges look like, I should be able to distinguish them well. Now, that would be really easy if estimating P of X were really that easy. Now, if Y, for instance, happens to be a continuous random variable, then you can still do this. You can still say, well, for any given Y, compute me P of X. So P of X given Y. But then it becomes extremely hard to, for instance, now integrate rather than sum over, P of X given Y. This becomes now an integral, because now P of Y is a density. And so your regression may actually be highly intractable, unless you pick a rather nice distribution, and we'll look at that. And just to drive home the message again, why this is a hard problem. Well, if I do bin counting, let's say I have bins for male and female, Chinese, German, French, Spanish, whatever, and so this is 10 bins. So I would expect to have to see, at least in Europe, maybe 100 observations to get something sensible. So a really good rule of thumb, and I want to underscore this is a rule of thumb and it can fail in so many amazing ways, is if you have n parameters, you want to have at least 10n data points. Can somebody give me an immediate example where this can go horribly wrong? Some application domain where this, yes?
Anything continuous.
Yes, anything continuous. Okay, so let's assume we restrict ourselves to discrete things, so some objects of whatever kind. Where can this go horribly wrong? Well, actually for pretty much any discrete object that there is out there. Because for most of them, you will have what's called a power law distribution. So if I was, who knows what a power law is? Okay, so a power law is usually given by something of the form P of X, where X is now the rank of the object really, is proportional to X plus C to the minus alpha. And alpha is the exponent of the power law. So in other words, what happens is that the rare objects are way less frequent than the frequent ones. Does somebody know a typical example for power laws? So basically a discrete distribution where this happens. Pardon? In social networks you have that. You have power laws on a graph. Something much, much more immediate, something that I'm using right now, namely language, has that property that the word distribution follows a power law. Money, so yes. If you look at wealth distributions for countries, you will often also find power laws. The exponent may then depend on the taxation laws and other historical properties of the country. Things like the number of times certain movies are watched, the number of times papers are being cited. So a lot of things follow those power laws. Okay, so let's take language. So it's quite obvious that words like and or and this and that and other stop words, they are very, very frequent. And words like, for instance, heteroskedastic are a lot less frequent. As in, some of you may not have heard the word heteroskedastic before in their lives. It basically means that the noise is actually, the noise level is variable depending on the covariance. We may actually encounter that at some point, but basically it's one of those really rare words unless you do finance. So what now happens is if I want to go and just estimate the frequency of words, right? And I sample maybe 1 million words, and I want to estimate the frequency of, therefore, 1 million divided by 10 of the first 100,000 words. Some very horrible things can happen. What will happen is that most of those words will never even occur just once in your 1 million sample. So the active vocabulary of most people is maybe in the order of 2,000. So 2,000 is if they're reasonably literate. Maybe somebody in the philosophy department brings it up to 3,000 to 4,000, but they'd have to be really good. Some politicians are known to have survived on less than 1,000 words. That can be actually by choice rather than by lack of ability, because this way everybody understands them. So you can use this as a tool, but that's it. What happens is that basically for most of the words you don't even see them once, so you will not be able to estimate their probability at all, or at least only upper bound their probability in a very crude way. So this is an example where just frequency counting fails horribly. Now in this case here, well, it just so happens that maybe with the exception of this class where we actually have 2 Spaniards in the class, so let's give them a big shout. But other than that, in general, probably this is the more common situation in a machine learning class here at CMU, right? So, and I think I'm the only German one here. I just, doctor the statistics, right? So what it basically means is that you have quite often not enough observations, you need to smooth. And what I'm going to show you now is how you can actually do efficient smoothing. Okay. So I hope this is a little bit clear at least that this factor of 10 can be quite badly off. It's nice if I have things like rolling a dice, but in those cases, if I have power laws, you need to be careful. So, and of course, what happens is if you use a lot of different categories, then those bins are almost all empty with probability 1. Now, you would wonder, why on earth would you care about stuff like this? Well, if you're looking at ads, these are attributes that you very, very much care about. So maybe, for instance, if somebody wants to, okay, let's say, for instance, I'm Tesla and I want to sell electric cars. Does it make a lot of sense to advertise in Pennsylvania? No, not really, because there aren't really any charge stations. So you may want to do geo-targeting and maybe target only the area around California and then maybe New York, right? So this is where the zip code comes in. Okay. Now, if I want to advertise My Little Pony, probably knowing what the gender of the viewer is matters. I'm not going to go into stereotypes, who likes it better. If I want to advertise, the next football or baseball game, well, the day of the week may matter a lot in terms of, when I show those ads. Okay. When I want to pitch the latest antivirus system, well, okay, it probably helps if it's Windows. So what I'm trying to get at is all those attributes, all those categories matter very much. And sometimes it may be the intersection of several of those. So if I want to get very accurate statistics, almost certainly I will not have enough data, even if I'm Google, Facebook, Twitter, or whoever else, to even fill all those bins. So we need to smooth. Continuous variable to make it even worse. So let's tackle the hardest problem first, namely continuous random variables. And this is called density estimation, as we already discussed. Namely, suppose I have effectively an infinite number of bins. And this is the sample of what I'm observing from the data. Now, these spikes are all at unit length. The fact that it's a little bit above 5% just has something to do with how many samples I drew. Yeah, I mean, they're obviously spikes going to infinity, but that's kind of hard to draw. So I could go and just bin things, right? I could split this interval going from 40 to 110 into maybe 10 bins and count for each bin how many observations we get. And by the way, I'm giving you a hint that this is the underlying density. Okay. So let's do bin counting. Okay, this is the underlying density. Here's the data again. A useful way if you want to draw samples from a distribution, right, is if you just draw them all on one line, you just get a lot of green goo smushed up here, and nobody can actually tell how many points you've seen. So one easy way of plotting this is by plotting as the x-axis, well, where you draw the thing. On the y-axis, you use basically some epsilon times a uniform distribution, for instance. So this way you get to spread out things a little bit more, and so it's a little bit easier for people to eyeball what's happening. Right? Just a simple visualization trick if you ever need to, visualize a univariate density, or rather a sample from that. Okay, so we count bins. And it sort of kind of works out okay, right? So there's 10 bins. And yeah. No. But it's really ugly because, well, why would you have this jump here? Can't we just be nice and smooth everything out? So in other words, can't we do something like this, right? Okay. Well, as a matter of fact, we can. But let's first go back to the probabilities. So what's actually happening here? If I wanted to perform, density estimation, then I can just invoke Höfting. And by Höfting's theorem, we know that the deviation between the expectation and the empirical average to be larger than epsilon is bounded this way. So that's actually kind of nice because it basically means that the accuracy per bin goes like order 1 over squared sample size. And furthermore, the number of bins only enters logarithmically. So rather than a 1, you really have squared log sample size, or squared log number of bins divided by squared number of observations. But it's still bad because the epsilon doesn't improve very much here. Now, what actually happens if you think about it is we are ignoring something fairly important here. Right? So let's just actually look at, this is basically what I just described. So you go and actually apply the union bound, use Höfting, and you get this inequality. That's what I told you before. Log number of bins plus basically the log of the confidence divided by sample size. Now, unfortunately, if I have d dimensions, right, then this will actually enter multiplicatively, right? If I have, let's say a is 10 to the d, then this will all of a sudden start behaving like d log 10. Right? And that's not so great anymore. So we are starting to see things falling apart badly as the dimensionality increases. And so the question is, can we do something? And of course we can. Namely, we can if we make the assumption that our density is not entirely arbitrary, but it is reasonably smooth. Right? So we basically are making the assumption that if we see all those spikes here, okay, that the truth is really this thing here. So in other words, we're making the assumption that everything is nice and continuous. And that means that the union bound that we took to obtain this result, which is basically treating each bin independently and assuming worst case that each bin can conspire against you in any arbitrary ways, is probably way pessimistic. So this is effectively also something that we wanted to know to some extent in the 41 Shades of Blue homework, right, where effectively we were asking about whether it's really the case that adjacent shades of blue would lead to not very similar click-through rates, and therefore you can actually apply exactly that smoothing argument. So this is effectively what you want to exploit. Okay. Any questions about the conceptual part here? Because those bins are not independent, really. At least, if reality is nice to me. Okay. Any questions so far? Okay. Sorry, yes?
So what reason do we have to believe that the continuity argument holds? Or let's say if we have like a continuous random variable and we're considering bins,
Okay.
how do we know that our bin selection is good with respect to like the frequency constants?
Yes. Okay, so let me just restate the question because it's otherwise not recorded. So the question was, what reason do we have to believe that what I just said is actually true, that there is really smoothness in the density? Well, first of all, so that depends very much on the problem that I'm looking at. So, for instance, if you're trying to estimate purchase behavior based on income, it is a very reasonable assumption to make that having $1 more or less on your bank account, if you're sufficiently rich, will only influence your purchase decisions marginally. So therefore, you can assume that these decisions are a smooth function. Now, if I don't have that domain knowledge, then I have no reason to believe that. Okay. Now, of course, you can come back and say, well, how smooth can I assume that things are? And this is where, fortunately, things like model selection can actually help us. So this is something that you were already asked to use for homework number 2, basically to tune your parameters. And effectively, what we'll see is exactly the same model selection argument playing out to infer how smoothly you really should make things. You can do this, for instance, by using leave one out estimates, basically cross-validation, or you could also use theorems, which then will give you statements along the lines of no matter how smooth things are, but assume that they are smooth at some given unknown level. If I get enough data, I will achieve the optimal or near optimal rate. So the theory statements will be along the lines of, well, even if the universe doesn't tell me anything about it, but I know that it at least has that smoothness as a certain property, I can design an estimator which reasonably quickly will catch up to a situation where I would know everything and then actually achieve the optimal rate there. So those are usually the strongest possible results that you can derive. They don't exist for all types of estimators in all contexts, but they exist for a whole bunch of them. And this is usually a fair amount of work to get this. So we have a lot of really good statisticians in, well, basically the stats department who design that kind of estimators, and you should take a statistical machine learning class to learn a lot more about it. It's very exciting work on the theory side. But those theorems are essentially like wearing a seatbelt, right? You never want to have to use it in practice to actually build something, but it's really important that you have them. Just like you don't drive without the seatbelt, at least you shouldn't. You want to have the assurance that if you get enough data, your algorithm is going to do well. Now, for the practical purposes, you will probably use things like cross-validation to fine-tune the specifics, but you want to have that theorem as a guarantee that you will never do something really horribly wrong. Okay. I hope that answers the question a little bit. We'll actually encounter exactly that case in probably about 15-20 minutes. Thanks for the question. Okay, so let's smooth things out. And in a way, the simplest possible thing that you could do already works quite well. So the first thing that I'm doing is I'm writing out an empirical probability distribution. So the key point here is this delta xi of x. Who has seen a delta distribution before? I mean, not seen, but knows what it is. Okay. So a delta distribution is basically, and I'm being amazingly lax here, an object where if I integrate out with it, it gives me the function evaluation. Or in other words, the integral of delta x, let's say delta x0, f of x dx is f of 0. And of course, if I don't have 0 here but xi, then it would be f of xi. So this is really just a pointwise evaluator. Think of it as, well, the density that you get by just, drawing once and putting all your probability mass there. Yes?
So is this kind of a trick to treat continuous things like they were discrete?
Maybe rather treating discrete things as if they were continuous. Yes. 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 Yes, that's one way of doing this. And you can actually have situations where you, for instance, have a continuous distribution with a couple of spikes in there. So, for instance, you may get situations, so this actually happens in papers, mostly published in life sciences, where you have overall a continuous distribution of p-values. However, you will get a substantial spike in the p-values at the just near 5% level. That's just because, well, people will tweak their results until they just pass the muster such that they get it published. And in that case, it's entirely an anomaly. But for instance, you may have things like, let's take an income distribution. And let's take a place where the minimum income is, let's say, $10 per hour. So then you will get an income distribution that's essentially a continuum. And then you would have a spike at $10 per hour simply because, well, nobody's allowed to pay less. So this is something where you could have a continuous distribution with a spike. So this is actually an example of something that's very common in statistics, in Bayesian statistics. It's called spike and slab. So just Google spike and slab, and there is very nice work by Ishwaran and co-workers on that. So this would be a cool subject for an advanced statistical modeling class, if at some point you take one. Okay, so now we have this empirical probability distribution, and it's ugly, right? It's basically that. It's a couple of spikes. Now, of course, if we see slightly different instances, like here, this breaks entirely because it just outputs 0, and for the other things, it outputs infinity. neither of which is particularly helpful. So the idea is, let's just convolve this with a smoothing kernel. Smoothing kernel is a glorious way of saying, let's pick some bump. And you can pick this, or you could pick something like that. And you can basically pick pretty much anything you want. And as it turns out, the particular shape of that smoother isn't so important. How large it is, however, is quite important. And we'll see that. So what we do is, therefore, we transform the sum over spikes into a sum over bumps, these terms here. And here are some 4 examples of what you can use for a density estimate, for a smoothing kernel. You could use a Laplace. You could use a Gauss. You could use an Epineshikov, which is basically just a parabola upside down and cut off. Or you could do the dumbest possible thing, namely just the uniform density. You would say, well, you know, within the interval between -1 and 1, it's 1/2, and outside it's 0. Can somebody tell me a good reason for not using the Gaussian kernel? A good computational reason.
It goes to infinity.
Fun?
So it goes to infinity. You cannot basically integrate.
Okay, so you cannot integrate. Well, okay, for Gaussians, usually people have worked out a lot of integrals 100 years ago, so we can be lazy and rely on 100-year-old books, or more recently, basically, Mathematica or Maple to solve the integrals for us. But the going to infinity part, you're on the right track. It makes computation extremely unpleasant, because no matter where I want to evaluate my density, do I actually have to sum over all those terms? So in practice, I will probably end up truncating anyway, so I might as well get over with it and just use something that has compact support. There were some comments here in the back. Yes?
It goes to 0 only at
It goes to 0 only at what? Yes, so that's the point, that it does not have a nice compact support. And this makes computation really hard. Because if I have a whole bunch of points, let's say here, and I want to evaluate things over there, then I have to really look at the relation between this point and all those red guys in order to find out what's going on. Whereas for the Epineshikov, maybe it would mean that I would only have to, look at these points in that neighborhood. Yes, there was another comment? It's not causal. I'm not sure how this currently relates to causality, because we don't have any causal dependence between random variables here at all yet. So what you're possibly thinking of is when you are filtering a signal and you're convolving it with a Gaussian, then we will get things that are not causal. Yes. So that's a small aside. This is something where I am basically taking a time series. So I have an ordering in which I'm observing certain, events. And if one of those events causes the next and the next and the next, of course, moving some of the probability mass to before when I saw this event would entirely screw up my causal relationships, because then the child could cause the parent. I'm less concerned at the moment about time series, but just about general density estimation. So for what you're referring to, things like Markov models, which we will encounter in probably a month or two, will actually be much more meaningful tools. So we'll get to this. So hold that thought. It's a very good comment, and it's true in the context of time series. So what this also already tells you is, if I have additional knowledge about my domain, about how my data is generated, using something like a kernel smoother can give me horribly wrong results. So make sure you know what you're applying the algorithm to, rather than just blindly applying it to. Because otherwise, you get garbage. Okay, very good comment. So you've probably seen those functions. You don't need to memorize them. This is exactly what Wikipedia is good for. You basically just search for, kernel density estimation smoothing kernels, and you'll find those 4 and probably a few others, and nice pointers to books that actually describe them in a little bit more detail. So let's see what happens. Well, here's the data, and the red thing is the smoother. Okay. And by the way, this is the super awesome, complicated Python or MATLAB code to do the trick, right? You just compute the distances. You compute a Gaussian and sum over it. That's it. So those 2 lines are what I use to generate this red curve. So here's an estimate. Okay. Now let's take a kernel that's way narrower. This is getting exactly the question that we had before. How smooth can I assume that things are? Well, you can clearly see that this estimate is a lot better than that one, right? But if you squint really hard, you would actually observe that at the points where I'm seeing the data, I have those really high spikes, right? So, and if I just want to compute the likelihood of this red estimate, it's actually way higher than what I will get there. Right? So, intuitively, we all know this is the right thing to do. And we all know that this is insane. So how can we distinguish between, the real thing and insanity? Okay. So I've just tried to push this a little bit further. I've taken the same distribution. Okay, so there we go. And I've computed the kernel density estimates for kernel widths of size 0.3, 1, 3, and 10. And you can clearly see that while 0.3 and 1 are pretty useless, and maybe 3 and 10 are a lot better.
Is it the size of the kernel?
Pardon?
Is this the size of the kernel?
The size of the what?
What size matters?
Oh, it's the size of the kernel. Basically, whether you use that type of kernel, right? Or whether you use that. Right? They both integrate out to 1, even though it doesn't look like that with my drawing, right? But, what you basically should see is that if I use something extremely narrow, I'll get an extremely wiggly estimate like this one here. And if I use something much smoother, I'll get something like so. Okay. Yes?
Are they lambdas in Regression?
Sorry, it's either what?
Are they lambdas of Regression?
So in this case, I think I used a Gaussian. I believe I did. I don't exactly recall it, but whether you use the Gaussian or a Laplace would matter a lot less. And we'll see a picture of that. But the scale matters a lot more. So let's actually look at the kernel. So the kernel width, in this case, so basically how can I actually make a kernel wider or narrower, right? So what I do is I take my original kernel H, and this is just, centering it at point xi. So x minus xi, this centers it there, divided by r, scales it. So if r is large, right, this means I make this kernel really wide. Right? And then here, I need to, take into account that I just stretched my kernel, or squished it. And so what happens is that if r is really large, I need to divide by a really large number. Because if the kernel is really spread out, the density cannot be very high at any given point. Okay. The exponent d is simply the dimensionality of the data, right? So if I take the kernel and spread it out very much in 1 dimension, okay, I pay a little bit. If I spread it out very much in 10 dimensions, multiplying the kernel by a factor of 2 in terms of width gives me 1024 as the rescaling in this case, right? So you can clearly see that scale adjustment has a much more dramatic effect if I work on very high dimensional data. And things can go wrong either way. If I pick a really narrow kernel, it'll overfit. So this is exactly the type of overfitting that we saw back when we basically did polynomial regression. Remember, we also had things that went to infinity. They don't have to go to infinity for overfitting, but quite often you will get very undesirable extreme values. Right? If we make something too smooth, it'll basically just smear everything out and we will lose all the signal. So the issue, therefore, is how do we actually select the model? And so the one thing that you could do is you could prove a lot of really nice theorems. We're not going to do that in 10701. That's something for the theory class. So let's select models. So what do we really care about? And this is a pretty crucial part of this class now. So maximum likelihood is something that will actually tell us how well we are doing on the data. So for instance, for a density estimation, we will care about P of x, which is given in this case by the product P of xi's, because I'm assuming that all these xi's were drawn IID from the same distribution. So minus log of P of x, which of course decomposes quite nicely, would be, well, the negative log likelihood, and I may want to try and minimize this. Now, finding a scale, sorry, there's a typo there, that actually maximizes P of x, well, this will, lead to all data points really corresponding to individual peaks. So basically each data point is then for its own, and I can make this kernel as narrow as I want, and therefore I will automatically maximize my likelihood. So that's what's going on here. Basically every single data point corresponds to this crazy high peak, and so my likelihood will go through the roof. And what happens therefore is that, on the test set my density will essentially be 0, and on the training set it'll be essentially infinity. Okay. So we are basically not doing ourselves favors by using all the training data to come up with our density estimate, because then we have nothing to really calibrate how well we are doing. Yes?
So you're taking the maximum likelihood with respect to the data we have, right?
Yes.
Can we do something like the maximum likelihood over all possible distributions given the data?
Maximum likelihood over all possible distributions given the data? Well, I could do that. That wouldn't really help me very much, because even a restricted set, like, well, all possible distributions that are given by, for instance, a Gaussian density, just with different scales, will already overfit like crazy. So increasing that set even further will make my life even more horrible. However, what you could do is you could have a prior over all possible values of the kernel, and then you would get a Bayesian style estimate for this. You could do that. Or you could use, for instance, things like leave one out, and I'll walk you through that in a bit more detail. Of course, the opposite is equally bad, where I just have, something very, very smeared out. So what I want to do is I'm interested in doing model selection. So one thing you could, for instance, do is you take all your data, and so let's say this is all my data, and I'm going to leave out some part of it. It's a random subset of the data. I use the red bit to tune my model. Let's say this is x. And then I evaluate on x prime. And I basically check how well I'm doing on x prime by performing all sorts of crazy operations on X. Now, if I do this for only a single value, a single choice of parameters for X, that's perfectly fine, because basically then the numbers that I'm getting on X and X prime are independent of each other, so everything is good. However, if I perform a lot of different tests on X prime by manipulating X appropriately, I'll run it exactly into the multiple testing problem that we already saw with the jelly beans, right? So it's the green jelly beans cause acne. Just because I tested for often enough, I managed to possibly get lucky at some point. Now, what you can also do is you can use learning theory to, for instance, look at all the possible choices that I can apply to my model, and then look at how much the empirical average deviates from the expectation if I, for instance, take the supremum here over all functions f in some class or all densities in this thing here. And so I'll need to make pf dependent on it. Yeah. So I'm just indexing p now with f, and I can try bounding things here. Can somebody tell me things that could go possibly wrong if I did this? Yes?
It depends how you split up your data. If you have a time series and you split off the end, then that's not actually capturing those.
Yes. So I may have dependent random variables, in which case a lot of this reasoning just goes out of the window straight away anyway, unless you're very careful. Okay. That's a case where pretty much all the things that I'm discussing right now are not going to help you a lot. You need to be extra careful. But now even let's assume I have IID data. One of the things is obviously, let's say it's really, really expensive for me to to obtain the data. Let's say, for each, let's say each of those XIs are a patient, and it costs me $1,000 to obtain the data, and I have 100 patients. If I leave 30 of those patients out just for validation purposes, I've just spent $30,000 only on model selection. And so I'm not really squeezing all the information out of those 30 extra patients that I could or should be doing otherwise. So in other words, how can we make it so that we get all the information out of all the patients by and large? Yes?
Wouldn't you do several splits and then try on one and the other and then?
Absolutely. That is exactly the solution. So what you suggested is called, for instance, k-fold cross-validation, or then in the most extreme form, and with the patients you would probably want to do that, leave one out. So a leave one out estimator is a perfectly reasonable thing to do if you have 100 patients and each of the patients costs you $1,000 to obtain the data, because their computation is cheap compared to that. On the other hand, if I'm Google and I have 1 billion users, doing leave one out cross-validations over 1 billion users is extremely expensive unless you find some very good approximations of what you would be doing. So in the case of, let's say, Google, you may actually want to say, well, I'll probably get enough statistical confidence if I validate on 1 million random users and I train on the remaining 999 million users. So in those cases, a validation set may be perfectly reasonable. If you, on the other hand, paid really a lot and you have a small data set, then you throw all the computation at it that you have. Okay. So the issue is basically you really want to be able to squeeze all the information out of it, and on top of that, the learning theory results are usually non-trivial to obtain. Okay. So I'll show you one example of what can be done. It's called leave one out cross-validation. So the idea is basically, let's go and use almost all the data to estimate the density. Right? And then I'm going to use a single instance to estimate how well it works. I can do that. That's very, very easy in the case of kernel density estimation because, well, all I have to do is I just have to sum over everything besides xi, right? So that's this thing here. And now, rather than n observations, I have n minus 1. And for good measure, I take the log of that. Okay. So this is now a random variable, which in expectation is going to give me the expected log likelihood. Right? If xi was, independently drawn, I could test over an infinite number of them. Well, this would be good. Here's a problem. Since I just have a single number, this thing has a very large variance. So I will get a almost unbiased, and the almost unbiased is because of the fact that I'm using n minus 1 rather than n observations. So, but this is something you can ignore in practice. But you have basically an essentially unbiased but huge variance estimate. Now, what do we do in order to reduce the variance? Well, we average. So what you can do is you can basically average this quantity over all the data. And the good thing is for kernel density estimates, this is trivial to do, right? Because we already know how to compute this entire sum. After all, this is basically K, a big matrix of kernels, times 1 as a vector. This gives me the entire probability estimate vector, 1 over n. And now in order to correct for a single term, I just need to add it back in and rescale. That's what we have here. And then I just subtract this term here. Now if you squint at it hard enough, you see that this is the very contribution that actually led to those spikes, right? Because essentially, if I make the kernel narrower, k of x and x, or k of x and xi, is exactly where that peak will be the highest. And what I'm doing, therefore, is I'm just correcting for the diagonal terms of this matrix here. This matrix. And so, the very intuitive argument of, well, you really shouldn't have those diverging terms here on the main diagonal, leads me to a reasonably principled estimator. Okay. And so what I then do is, I just sum over all the i's, over I here. Yeah. And let's go and plot this thing. So this is basically for different kernel widths, the leave one out log likelihood. By the way, you can use the same argument for k nearest neighbors, trying to validate k. You can use it for polynomial regression, any of those things. Okay, and what we see is this thing is fairly well behaved around here. So basically anything around there is probably a reasonable estimate. It's less important whether you pick this value or that value or that value. What you really want to make sure is that you don't end up here. Right? Because, this is log scale. So those estimators do extremely poorly. Whether you pick the best or the second best value isn't quite that important, but it's really important that you don't screw up catastrophically. Okay? And so let's look at it. Does it look pretty? Well, no, not really, right? It's kind of quite jittery. But at the very least, it captures overall the distribution. Now, sometimes, leave one out is very expensive. So what we do instead is we basically just use k-fold cross-validation. In this case, for instance, you partition things into k blocks. Typically, k equals 10. And you use 90% of the data to evaluate how well you do on the remaining 10, and you cycle through. Question?
In the one-out cross-validation from before, you basically
one parameter and then see how it behaves for leaving one out. So every time, this means like you perform this for
Yes.
the amount of that. Like for
Yes.
n.
Yes.
Okay.
Yes. So basically, suppose I was, yeah. So this is so basically what the question is: isn't this crazy computationally expensive? And it was formulated in a very polite way. Thank you. Yes, it is. So in other words, if I brute force go and evaluate this thing, this function here, for all possible values of the kernel width, then I can spend a lot of time, which wasn't a big deal here because I used maybe 100 observations or so, and computers are fast, and if you write code without the for loop, you will get decent numbers. So you really want to use computational savings here such that you don't have to recompute all the values from scratch for every value that you take. Sometimes you can bound things, and there are then all sorts of nice computational tricks when you basically use a reasonable bound or a proxy for what your leave one out estimator is supposed to give you. So that can help. Or you just do tenfold. Now, do I have to do this for... So suppose I have two parameters that I can choose. It's the kernel width, and then maybe which kernel I use. Well, then you would actually have to perform, well, in the most naive way, grid search over both things. Is that a good idea? Probably not. So you probably want to actually then use some nonlinear function optimizer or maybe a Bayesian bandit algorithm to figure out which parameter combination to pick. So there's a fair amount of research by now that goes into this. I think one of the open source packages is called Spearmint. I'm not going to comment very much about how well or not well they do this. But so Nando de Freitas probably has some more interesting and more relevant work on this. But let me just give you the pointers. And then there's this thing called Spearmint. And yeah, I would probably look at his work first. So this, of course, requires a whole bunch of tools that we haven't even discussed yet, essentially bandit algorithms and so on, because you really don't want to have to go and evaluate this function everywhere for all possible parameter choices, because this very quickly gets you again into a cursive dimensionality setting. So you want to optimize reasonably well. And yeah, the theoretical underpinnings are, for instance, by Luntz and Brailovsky, and they showed that the leave k-out estimator is almost unbiased, and the almost comes from the fact that I might be training only on 90% rather than 100% of the data for a leave, basically for a tenfold cross-validation. Okay. Now, any questions so far about the density estimator? Okay. No questions? All clear? Good. And let's move on. So let's actually use this. So I did not find a picture of Mr. Nadaraya, but I found a picture of Geoff Watson, who's one of the co-inventors of the Watson-Nadaraya estimator. These were actually two papers that came out essentially at the same time. And if you think about it, the idea is amazingly simple. This essentially works as follows. So let's say I want to estimate P of x given y. I can do that, maybe with my kernel density estimator. And I also do this for P of x given y equals -1. So I'm basically performing a density estimate for apples. I'm performing a density estimate for oranges. Now, if you think about it, what I've just done is I've actually just built a classifier. Because by base rule, P of y given x is, of course, P of x given y times P of y divided by P of x. Okay. And so now what I can do is I can just plug those terms in here. Right? So who wants me to derive exactly how we get there? Nobody? Everybody's clear? Okay. 1, 2, 3, 4. Okay, good. I think we have enough people who want me to derive it. Don't be shy. The point is, if you don't say you want me to derive it in detail, I will not do it. So, okay. So remember what we had is P of x is 1 over m sum over I going from 1 to m k of xi and x. Right? That's just our standard density estimator of P of x. Furthermore, we know that P of y, let's say P of y equals 1, or just in general P of y, is, in the simplest case, my over m. Right? That's just, number of times, for instance, I see apples versus total number of occurrences of apples and oranges combined. Now, P of x given y is simply, well, now I only have those observations that really show up in the set, so I have 1 over my times the sum over I going from 1 to m, k of xi and x, and I have to impose the additional condition that yi equals y. Okay. So now, all I have to do is I just have to plug in basically P of y given x is just P of x given y times P of y divided by P of x. Now if I do this, you can see that the my terms cancel out. The m terms cancel out. Yes?
Just to make sure I'm understanding this here, P of x is going to be something like, I don't know, the weight of the orange, the weight of the fruit. So P of x given y is the weight of the fruit given that it's a
correct. It could be the weight, the size, the spectrogram. It could be the picture of this thing, right? Now, whether a Gaussian model for the picture would be particularly intelligent, well, I don't think so. That said, people actually use it. So it could be any attributes that you have about that object in front of you. So, how rounded it is, which might help you distinguishing apples from bananas, but basically anything you want. And so now, all I have to do is I just have to take these two ratios, right? Because everything else cancels out. And so, I get nothing else than sum over I going from 1 to m with the condition that yi equals y of k of xi and x divided by sum over I going from 1 to m k of xi and x. So in other words, I just use my density estimate for, well, let's say the apples, versus the density estimate for the apples and oranges combined. And quite nicely, all the normalizations go away. Yes?
Here, the estimation we have of the probability of y is as simple as that because it's binary. If we had something more complicated, we'll have to have something like the probability of x with these groups.
Well, actually, not entirely. So here, I didn't actually exploit that we had a binary distribution. All I did is I just said, well, P of x given y is just 1 over my. So I could have, 100 different outcomes here, right? I could have apples, oranges, bananas, and pears, right? Okay, it's 4, not 100, but basically all you do is you restrict your sum only over the appropriate terms.
I mean for the second line, like the...
Well, again, that would be, let's say I have, 100 fruits in total, and I see 16 bananas, then P of banana is, 16%, right?
So, yeah, like, I see the most simple we can have.
Yes, so you could use a smooth estimate for that too. So you could, for instance, use a Laplace smoother. And then you would get slight correction terms here, right? So if that happened to be the case, you would get something like, basically M would now turn into M plus a smoothing term. My would turn into something plus a smoothing term. So you would get essentially correction terms where if you have enough data, those correction terms will all just go to 1 and therefore disappear. But for very small minority classes, they might actually matter quite a bit. It's a very good question. You can probably just check that on with pen and paper afterwards for yourself. It actually gives you a very nice estimate. Yes?
I'm sorry, I don't understand exactly what the operation k of xi comma x is. Is the kernel evaluated at...
Oh, okay. So what is k of xi and x? Well, this is just a lazy shorthand for writing, for instance, h of xi minus x divided by r to the minus d. And so r is the scale, and this is basically defined as k of xi and x. Yeah, thanks for asking the question. I should have clarified that before. Yes?
Should it be x minus x because it's centered at x?
If the kernel is symmetric, it doesn't matter. In most cases, it will be. And so the only thing you need to be is consistent. And then, you just have to make sure you get the left versus right-hand symmetry right. So, by the way, when would it make sense to have something that is asymmetric? Or maybe that actually depends on the actual value of x rather than just this? Yep?
Maybe if you have some sort of cutoff or boundary to your data.
Perfect. That is exactly where you would care. So, for instance, if I have, okay, well, maybe not counts, but if I have energy levels, right, in a physical system, since I can't have negative energy, I would actually have that as a cutoff. So you can basically, or if your domain got transformed, then you would automatically have asymmetric kernels, right? So they may be symmetric in the log domain, but not in the actual domain. So there can be a lot of those cases. Very good questions. So now the next trick is then that we can ask, what's the decision boundary? And there, I do exploit the fact that, this is basically binary. Because what I can do is I can simply write P of y equals 1 given x minus P of y equals minus 1 given x, right? Because what I can do is, exactly where this thing is 0, this is the boundary where I cannot decide whether I have positive or negative observation, right? It's not normalized, of course, but it tells me, where that boundary is. Now, if you plug this in, it turns out you can write it exactly like this difference, right? So that was, in a way, the next key observation. So you can just write it as, yi equals 1 or yi equals minus 1, and I just take the difference. Okay. And then the last observation in this was, I can just pull those yj's out of the ratio. Yes?
And so in this case, the decision boundary would be the sign?
Exactly. So the decision boundary is basically where this function here equals 0. So I could have f of x to be this, and y hat would be sine of f of x. And that's, of course, the best thing I can possibly do. You have some more questions, do you?
And if you instead had used the labels y equals 1 and y equals 0, then the decision boundary would be 1/2?
Yeah. So I'm making my life easy here by just making sure that I name the labels 1 and -1. Yes. So you can work out, of course, how you get the affine transform. But I'm being a lazy bum here, and I like to keep my notation simple and my code simple. That's why I'm picking 1s and -1s. Generally, statisticians look at classes 1s and 0. Machine learners use 1 and -1 unless defined otherwise. Also, usually, frequentists use sample size m. Bayesians often, or more generally, statisticians may use L as their sample size. So these are the subtle clues of notation. And you have to be a little bit careful about what you do. So usually everybody assumes that epsilon is greater than 0. Try that out on your friendly mathematician. Write it on the windscreen of his car, and he will wash it. Try it and test it. One of my fellow students when I was at university had a dirty car, and we got him to wash it this way. But in any case, so I'm using 1 and -1 here. Okay, now, if you squint at this hard enough, what you can see is actually that this is effectively like a local weight. You can see that those weights here have to sum up to 1, right? So I could basically call those things here wj of x. And what therefore happens is that if I want to evaluate, my classifier at some location x, I just take a weighted average over the yj's being 1 and the yj's being -1. And if the 1s prevail, then I say it's positive. If the -1s prevail, I say it's negative. So this is a very different way of looking at what we got through Parzen windows, right? But it's an extremely useful way. So let's actually see what happens in practice. So here's the data again. This is what the Watson-Nadaraya classifier does. This is basically just looking at the signs. So again, the code is insanely complicated, right? 2 lines. So by the way, why doesn't everybody use Watson-Nadaraya classifiers given that the code is so simple? Can somebody tell me some arguments why you should spend more than 2 lines? Because after all, you could say, hey, I know how to do classification. I can go home. I don't need to listen to the rest of Alex's lecture. Why can't we just stop here? Fun?
Imbalance?
The imbalancing is an issue. So there are all the issues about the distribution. But even in the IID binary classification case, why can't we just stop here? The overfitting, so the model selection, that's an issue. Yes. A much bigger issue is it's an okay classifier, but it's not the best one because it actually inherently relies a lot on more or less density estimation. And secondly, as I get more data, this classifier will get extremely slow. So it's the same problem that we had with nearest neighbors. And I basically need to compute the neighborhood for this point to everything else. Right? I'm comparing this with everything else. And that's what makes it insanely expensive. So now, however, this entire idea of weighted averages, right, is something that carries a little bit further. And this is basically where then the Watson and Nadaraya part came in. I think Nadaraya did the part for regression and Watson did it for classification. And I said I was unable to find a picture of Mr. Nadaraya. Those papers were written in the 60s, I think within the same year or 1 year from each other. which is essentially simultaneous in the time before archive and the internet. So here's the difference, right? So we basically, for classification, used these weighted averages. And now you could say, well, rather than ones and minus ones, why not use the same trick just for any regression scores? Why not? I mean, after all, I get, local weighting, all the weights sum up to 1, so I could just do that. And in fact, why not? Let's do it, right? This is the truth, the red line. The blue dots are the data that was sampled. So it's basically the truth plus some noise. And the green line is what you get for the Watson-Nadaraya regression estimator. And by and large, it does a pretty decent job, right? I mean, it's not fantastic, but it's not horrible. It's kind of questionable out here. And that has a lot to do with me simply not finding any data points here. But it's not too bad. Yes?
How is this different from a Gaussian process or something like that?
Very good. So how is it different? Well, it's very different insofar as in a Gaussian process, I actually use correlations between observations to get a weighting. And I can actually get negative weights in some cases. So we will see the same picture shortly again, well, maybe in a month or so, where we basically use a Gaussian process to regress. And what we'll see is a Gaussian process is way more powerful in higher dimensions. Okay. Now, given that the next lecture is already here, let me just very quickly skim over a few additional issues. And so there's something called Silverman's rule. So basically, suppose I want to estimate the density of people, in the United States. Then I can use a smoothing kernel. And the problem is that I have to do well for both Kansas and New York. And in New York City, I may have very high density, but I still have variations in density, let's say, between Brooklyn and Manhattan. And on the other hand, if I use something as narrow as what I used in New York, it will fail miserably in Kansas, or Alaska for that matter. So what you basically want to have is you want to have a smoothing kernel that is very narrow in regions of high density, and it's very wide in regions of low density. But this is weird because it pretty much assumes if I knew the density, I could estimate the density really well. Duh. So what we need, therefore, is an extremely cheap way of sort of kind of getting a proxy for what the density might be like. And what you can do is you can basically just look at the k-nearest neighbors and use them to get this estimate. And so what you get is a non-uniform bandwidth estimator. And, well, basically what you see is an adaptive estimate which uses wider kernels where I have less data, will do a lot better. And yes, that's what it is, all that I had time to say. I will recap the nearest neighbors on Wednesday. Okay, thank you very much. If you could please stop the camera.